In this video, we'll discuss an important model for oligopolistic competition, the Cournot competition model. The model is proposed by Anthony Augustine Cournot back in 1838 as a model to understand the competition of large firms. The setting of the model assumes that the firms simultaneously choose their capacity levels or output levels, and the prices are consequently determined by the market through the demand. You can think of a Tesla and Volkswagen both decide how many electric cars they will produce in the next 5 years. And once the production facilities are built, they will produce the amount and offer incentives and discounts as needed in order to sell all these cars. The simultaneous choice assumption is important for us in this model, and would mean in the Tesla and Volkswagen example that these firms don't observe each other's choices while they make their own decisions, but they hold some belief about what their opponents will do. More specifically, the model assumes that the firms produce identical products, such that the consumers cannot distinguish one's product from the other, and the firm cannot directly control the price of their products. Perhaps because the firms have a high inventory cost, so they have to sell all the products, or because the pricing is controlled by some downstream retailers. The implication is that the demand side eventually sets the price of the good, and the firms react to the price and to each other's output by choosing their own output levels. As an example, we'll consider a simple case of Cournot competition with two identical firms competing in the market. We assume that the inverse demand function in the market is the following. The price of the market is determined jointly by the output levels of each firm, and the price is decreasing in the total output level. So we have a standard downward sloping demand curve. In this case, the demand curve is actually linear. Each additional unit of output lowers the price by 2 units. It doesn't matter if it's coming from firm 1 or firm 2. You can see that these two quantities are perfect substitutes, which reflects the assumption that the two firms are producing identical products. So the effect on the market price only depends on the total amount of outputs, as opposed to who produced them. We also assume that these firms have identical costs with no fixed cost, and linear variable cost, like this. So their marginal cost is just a constant of $2 or 2 units. We can think about the possible outcomes of this model for a little bit before diving into the analysis. We know that a profit-maximizing firm would choose the output level such that the marginal revenue is equal to the marginal cost. The marginal revenue, which depends on price, depends on the firm's own output level because of the downward sloping demand function. And this is very similar to the monopoly model. But what complicates the issue further here is that the price, therefore the marginal revenue for a firm, let's say firm 1 here, also depends on the output level of its competitor, firm 2. So the belief about the opponent's choice actually matters for the firm's own decisions. If I believe my competitor will produce a lot of outputs, then the price is likely to be low. So my marginal revenue will be lower. And therefore, my output level is likely to be lower, facing the same marginal cost. But then, if I reason that my opponent will think in a similar way, wouldn't it be better if I produce a lot of goods to somehow preempt my opponent? Well, all these strategic concerns make it very difficult to reason through the model and find the plausible outcomes. So our way forward is to appeal to Nash equilibrium, which will help us find outcomes where the firms play best responses according to their beliefs, and their beliefs actually turn out to be consistent to these outcomes. We can translate this model into a basic structure of a game. In this example, the game would have 2 players, firm 1 and 2. The strategy for each firm will be no longer a binary choice, but a continuous choice of any quantity level. We'll call them QI, where I is an index for the firm. either 1 or 2. And the payoffs for the firm will just be pi I, again, 1 or 2. In particular, the profit for any one of these firms, firm 1 or firm 2, will just be, again, the revenue of the firm minus the cost of the firm. The revenue is just price of the market times the quantity sold by this firm itself, and then minus the cost incurred by this firm itself. We can plug in the inverse demand curve from this function here that was given in the problem, and that gives us 102 minus 2 times the total quantity times output of this firm itself, and then minus its cost. And here we're using the notation of I and J to index each firm. So I stands for one firm, and J stands for its opponent. In other words, when I is 1, J is 2, and when I is 2, J is 1. This way, we can use these notations to write very similar objects once and only once. There's no need to write essentially symmetric objects twice, one for firm 1 and the other one for firm 2. Notice here that in firm 1's profit, the quantity that matters is only the output of firm 1. For firm 2's profit, the output relevant is going to be the quantity of firm 2. This makes sense because each firm only collects revenue on their own outputs and incur the cost on their own outputs as well. In other words, the only channel that the opponent's output can affect one firm's profit is through the price, which is here. Clearly, as we reasoned above, the belief about the opponent play matters. As firm I, my belief about firm J's output level affects my marginal revenue, and therefore influences my decision. Because there are so many different output levels out there, the belief can be anything. So how we pin down some outcomes that are consistent, we'll use the concept of Nash equilibrium. From the previous video, we understood that a Nash equilibrium is just a set of requirements. It requires that each firm plays their best responses given their beliefs about their opponent's play, and it requires their beliefs to be consistent with the actual strategies played in that outcome. In this game, it would mean that each firm chooses their best responses in output levels to maximize their own profits, given their beliefs about how much their opponents will play. And we'll use hats here to indicate the beliefs held by each firm. In a Nash equilibrium, these beliefs will turn out to be correct. And the idea is basically the same as in our Prisoner's Dilemma game or coordination game. But the strategy is no longer a binary choice, but a continuous one. This means that we don't have a clear payoff matrix to look at. So how do we find the Nash equilibrium? We're going to follow more or less the same process as before. First, we will let the beliefs to be somewhat arbitrary. And then we'll try to find the best responses for each firm given these arbitrary beliefs. This will give us a best response function that depends on the arbitrary belief instead of a fixed choice. If you think back to the coordination game in the previous video, the best response is in fact a function. If I believe you'll play new, I'll play new, and if I believe you'll play old, then I'll play old. This is a function where my strategy depends on the belief. And so here, the best response functions are just going to be slightly more complicated. Once we have the best responses, we will impose the second requirement of Nash equilibrium. That requires the beliefs to be correct or consistent with each other's best responses, so that what I believe you would produce is in fact what you will produce at your best interest, and vice versa. It turns out that this condition will help us pin down the equilibrium outcome. And in the Cournot game, the equilibrium outcome turns out to be unique, which is quite surprising given how complicated this game is. Now let's delve in and solve for the Nash equilibrium of this game. To find the best responses, we write down the firm's payoffs again, copied from the setup of the model 2 slides ago. And the firm's best response is just a strategy that maximizes the firm's payoff given its belief about the opponent's strategy. By the simultaneous move assumption of the Cournot model, each firm does not actually observe the other firm's output level. So each firm, I, would form some kind of belief, which we'll call QJ hat here, where J indicates the opponent and hat indicates the belief. It is important to understand that because of the simultaneous move feature, the opponent firm wouldn't see firm I's choice while it makes its own decision. So firm I understands that whatever QI it chooses won't directly affect J's choice. As a result, I's choice wouldn't change what I believe J would do. In other words, the partial derivative of the belief about what the opponent would do does not change with the firm's own output choice, QI. This is a key feature of how the simultaneous move assumption plays through the algebra later, and it is essential they understand this point. Now let's take the perspective of one of these firms again. Let's say firm I. Given any belief about the opponent's choice, or QJ hat, which is arbitrary now, firm I's best response is determined by the first order condition of this objective function. So we'll take derivative of this profit function with respect to QI, because the derivative of QJ hat with respect to QI is 0, we found this particular derivative. And this first order condition determines that the QI that satisfies the first order condition is our best response. Now we can rewrite QI from here in terms of QJ hat and all these constants. And it is in fact unique, which is equal to 25 minus half of QJ hat. We can read into this expression a little bit. It says that my best response is to produce 25 units of output if I believe your output will be 0. And for each additional unit I believe you will produce, I will reduce my output by half a unit. This reflects our earlier intuition. If I believe my opponent will produce a larger amount of output, then the market price will be lower. So my marginal revenue will be lower. And that leads to a lower optimal output level for me. Now we have the best responses. How do we solve the Nash equilibrium? Here we have the best response we just derived. Note that the best response applies for both firms. If I is 1, then J is 2, and if I is 2, then J is 1. The benefit of using the IJ notation again is that we only need to solve this problem once, instead of solving each firm's problem in turn and gets to basically very similar outcomes. But to see how it goes from here, it is useful to write them out as 2 separate firms' problems. Once written out, we have 2 equations, one for each firm's best response. And in these 2 equations, we have 4 unknowns. The 2 best responses Q1 star and Q2 star, and the 2 beliefs Q2 hat and Q1 hat. Because these beliefs are arbitrary, they can be anything, and each firm will just play their best responses. So we can't pin down any outcomes yet by just imposing that the firms will play their best responses to their beliefs. And this is exactly where the second piece of Nash equilibrium comes into play, which requires that the beliefs for the firms to be correct in the equilibrium outcome. This means that what firm I believes firm J will do actually turns out to be firm J's best response. This means that we're imposing that the hats are in fact the stars. By imposing that Q1 hat is equal to Q1 star and Q2 hat is equal to Q2 star, the four unknowns in the system of two equations now becomes two unknowns and two equations, which means we can solve them uniquely through the system. And there we have it. By solving this pair of equations, we can find these two solutions where firm 1 and firm 2 both produce exactly the same amount of 1/3 of 50 units of good. And this is our Nash equilibrium. In other words, by using Nash equilibrium, we identified one unique outcome out of all possible outcomes of this model. This is an incredibly sharp prediction out of a very complicated environment. To better understand this solution process, we can try to illustrate these best responses and results on graphs. By solving the first order conditions, we found the firm's best response functions, which are these two expressions. And we can try to plot them on a separate graph, one graph for each one of these functions. On the left-hand side, we are plotting Q1's best response on the vertical axis as a function of its belief about firm 2's output, which we put on the horizontal axis. We see that it has an intercept of 25 units when Q2 hat is 0, and every unit increase in Q2 hat drops Q1 star by half a unit. Therefore, it has a slope of -1/2. On the right-hand side, things appear a little bit strange. We're plotting firm 2's best response on the horizontal axis, and it is a function of firm 2's belief about firm 1's strategy, which we put on the vertical axis. This is intentional, and I will explain it in a second. If you tilt your head, you can see that it is exactly the same idea as the function on the left-hand side. When firm 2 believes firm 1 will produce 0, firm 2 produces 25 units, and for every additional unit firm 2 believes firm 1 will produce, firm 2 will lower its output by half a unit. So given these two graphs, we really have two unrelated graphs or curves or functions, and four variables: Q2 hat, Q2, Q1, and Q1 hat. Just like the two best response functions. Simply requiring each firm to maximize their profits doesn't help us pin down any particular outcome, because the firm's beliefs are completely arbitrary. However, if we further impose that the firm's beliefs about each other's play have to be correct, which is the second condition in the definition of Nash equilibrium, then the beliefs are lined up with the best responses. And the vertical axis of each graph here becomes the same, and so do the horizontal objects. We just have Q1 and Q1 and Q2 and Q2. And now we will be able to grab one of these curves and just overlay it on top of the other. And this is where we turn the two equations and four unknowns with beliefs into two equations and two unknowns of best responses. And they lead to the unique equilibrium outcome, where each firm produces 1/3 of 50 units of output. Now we have solved for the player strategies in the Nash equilibrium of this game. But what do they mean in a competition model? We can find the market price level when the firm produces at these quantities. To do that, we just plug in these quantities into the inverse demand function, and then we can get the price of 35.3. Furthermore, we can find each firm's profit level by plugging the outputs and the prices into each firm's profit function, which is just the price of each unit in the equilibrium minus the marginal cost, which is constant for each firm, and then multiply by the quantity. As a result, we found that each firm's profit level is 555.6 units. In this video, we learned about the essential features of a Cournot competition model, where firms producing identical products to compete with each other by choosing their capacity or output levels. We apply the Nash equilibrium concept to identify a plausible outcome in the market, and found that the two firms each makes a positive profit in the equilibrium. We will compare this outcome against the monopoly outcome in exercises.